Okay, this is going to be the second video for section 6.8, and we're going to be looking at the divergence theorem. And it states that let Q be a solid region bounded by the closed surface S, orientated by the unit normal vector directed outward from Q. If F is a vector field whose component functions have continuous first partial derivatives in Q, then the double integral over S of f dot n ds, that's your flux integral, is equal to the triple integral over Q of the divergence of f dv. Recall that if f of xyz is equal to mi plus nj plus pk, then the divergence of f is equal to the partial derivative of m with respect to x plus the partial derivative of n with respect to y plus the partial derivative of p with respect to z. So we'll kind of go just a little bit over the idea of the proof. And so what we're going to do is we're going to consider a small box with sides parallel to the coordinate planes. Okay, so in our figure here, maybe it's an egg or something, so there's the box in there. Sides parallel to the coordinate axis. The box has the dimensions delta x by delta y by delta z. Okay. Looking at a face of the box, so we'll look at a face of the box with a center of x, y, z. The normal vectors are k at the top of the box and negative k at the bottom of the box. The dot product of f and k is p. Okay, now the flux out of the top of the box is going to be p, so that's the p of your vector field of x, y, z plus delta x over 2. So let me try to draw it a little bit better. So you can also see this image in your textbook, but you have delta z here, the center, x, y, z. Okay, and then we have here x, y, z plus delta z over 2. Okay, and so we're calculating the flux as p of x, y, z plus delta z over 2. And then times delta x, delta y. Okay, so that's out of the top of the box. And then out of the bottom of the box would be negative of that same thing, whether we're using our normal vector as k or negative k. So if you're using negative k, then your f dot n would be negative p. Okay. All right, let delta p be the difference between the values. So the value out of the top of the box and the bottom of the box. Then the net flux can in the vertical direction be approximated by delta p times delta x times delta y. Also, delta p times delta x times delta y can be written as delta p over delta z times delta x, delta y, delta z. Then if we let our delta x, y, z's get closer and closer to 0, then we have that is approximately equal to the partial derivative of p over delta z. With respect to, so partial of p with respect to z, and then times delta v. And then we can do a similar construction for the x and the y direction. And so the total flux is going to be partial of m with respect to x plus partial of n with respect to y plus partial of p with respect to z dv, which is going to be equal to the divergence of f delta v. We'll make slight correction here. This should be delta v there. Okay. All right, and down below here we have the flux form of Green's theorem. I believe we probably covered this a little bit earlier when we were looking at the Green's theorem section. So the line integral over c of f dot n ds. That'd be a flux over a curve. That's going to be equal to the double integral over the region R of partial of n with respect to x plus partial of n with respect to y dA, which is equal to the double integral over R, the divergence of f dA. That's the divergence theorem is Green's theorem for one higher dimension. Okay, so let's look at an example or two here. Okay, so let's use the divergence theorem to calculate the double integral over s of f dot n ds, so flux integral, and find the outward flux of f of x, y, z is equal to xi plus yj plus zk through the surface bounded by s, which is z equals 9 minus x squared minus y squared, where the z is greater than or equal to 0. So we'll go ahead and draw our paraboloid. Okay, so here's our paraboloid. And then we have outward normal. Okay, f of x, y, z is equal to mi plus nj plus pk. The divergence of f is equal to, well, partial derivative of x with respect to x plus partial derivative of y with respect to y plus partial derivative of z with respect to z. All those are going to be 1. So the divergence of f is going to be 3. So your flux integral is going to be equal to the triple integral over the region Q of the divergence of f dv. Okay. So I'm going to convert this to polar coordinates. So on the xy plane, we're going to go all the way around, so 0 to 2 pi for theta. The radius is going to go from 0 to 3 on the xy plane. And then remember, z is equal to z in polar coordinates, so we're going to be going from the xy plane all the way up to the hitting the parabola. So z is equal to 9 minus x squared minus y squared. If you remember, x squared plus y squared is r squared, so this is going to be equal to 9 minus r squared. So we got the integral from 0 to 9 minus r squared, the divergence of f, which is 3, times r, which is the Jacobian. And then, so 3r, the r is for the Jacobian, dz, dr, d theta, which is equal to, we'll slide the constant of 3 out, integral from 0 to 2 pi, integral from 0 to 3 of rz, evaluated from 0 to 9 minus r squared, dr d theta, which is equal to 3, integral from 0 to 2 pi, integral from 0 to 3 of 9r minus r cubed, dr d theta, which is equal to 3, integral from 0 to 2 pi of 9 over 2 r squared minus r to the 4th over 4, evaluated from 0 to 3 d theta. That's all going to be a constant, so we're going to slide that out. So it's going to be 3, and then 9 times 3 squared, it's going to be 81 over 2, and then 3 to the 4th is 81, so minus 81 over 4. Okay, integral from 0 to 2 pi of 1 d theta. And so that's going to be 3 times 81 over 4. That's what 81 over 2 minus 81 over 4 is going to be equal to. And then we integrate and we get theta, evaluated from 0 to 2 pi. And so this is going to simplify down to 243 pi over 2 is the flux. All right. I got one more example for you guys in this video here. Okay. So we're going to evaluate the double integral over s of the curl of f dot n ds, where s is bounded by the x equals 4, the plane x equals 4, z equals 9 minus y squared, and the coordinate planes. F of x, y, z is equal to xy cosine zi plus yz sine xj plus xyzk. Okay, so we're going to go ahead and draw our parabola. And we're going to stop it at x is equal to 4. Okay. So a double integral over s of the curl of f dot n ds is equal to the triple integral over q of the divergence of a vector field, which happens to be the curl of f. So let's calculate the curl of f. So I column, you have differential operator with respect to x, xy cosine z, j column, differential operator with respect to y, yz sine of x, and the k column, differential operator with respect to z, of xyz. Okay, so cover up the I column, and partial derivative of xyz with respect to y will be xz, and then the partial derivative of yz sine of x will be y sine of x. It's xz minus y sine of x. And remember the k component, I'm sorry, not the k component, the j component is going to be negative. Cover up the j column. Partial derivative of x, partial derivative with respect to x of xyz is going to be yz, minus the partial derivative of x y cosine z with respect to z will be a negative xy sine of x. Sine of z, excuse me. Okay, so yz minus negative xy and then sine of z. Okay, and then lastly, cover up the k column. Derivative of y sine z, derivative of yz sine of x with respect to x is going to be yz cosine of x. And then minus partial derivative with respect to y of the xy cosine z would be x cosine z. So yz cosine x minus x cosine of z, which is going to be equal to xz minus y sine of x minus yz plus, oh, we got 3 negatives. 1, 2, 3. So 3 negatives, the net result is negative xy sine z, comma yz cosine x minus x cosine z. Okay. Now we're going to calculate the divergence of our curl here. So this should actually say the divergence of the curl. Okay. The divergence of the curl. So take the derivative of xz minus sine of x. Xz minus y sine of x with respect to x. That's going to be z minus y cosine of x. And then the j component, we're going to take the derivative with respect to y, which is going to give us negative z, and minus x sine of z. And then the k component, we're going to take the derivative with respect to z, so we're going to have y cosine of x, and then plus x sine of z. Okay, so the z's will absorb, the y cosines of x absorb, and also the x sines of z absorb. So now we're looking at the triple integral over the region Q. Divergence of the curl is going to be 0, and so the divergence here is going to be, the value of this flux interval is going to be 0. Okay, and this is a result actually. The divergence of a curl of a vector field is going to be 0 here. Okay, all right. So that's it for this video. We'll see you next time.